Hello everybody and welcome to our next video on Unit 8, which we're going to talk all about buffers. Buffers are super important. I know you've heard me talk about this quite a few times already, but in the chemistry world, we need buffers for our life, for lots of different chemical processes. So this is quite an important concept, and a lot of actually what you are required to know for this unit deals a lot with buffers. If you look at that CED, I think there's at least 2 or 3 scenarios that deal with buffers. Anyway, neutralization reactions are the fastest and one of the most common reactions in chemistry. So when we have that transfer of a proton from acid to base, very common reaction, typically is how a lot of indicators work as well when they change color in solution. And they happen very fast as well. But a lot of these neutralization reactions, these reactions of acids with bases, however, are not just with strong acids or strong bases. A lot of times these will deal more so with weak acids or bases. And of course, that's only because there are 6 strong acids and 6 strong bases, and then a heck of a lot of weak acids and weak bases. So we're going to deal more so with reactions that involve weak acids and bases. However, we have to also talk about what a buffer is, because buffers deal with the reaction with weak acids and weak bases. And in particular, these have a couple of different properties that make them unique, what a buffer is. So a buffer is a solution of known pH that's characterized by its ability to resist changes in pH when small amounts of acid or base are added to it. And these are going to be a mix of a weak acid and its conjugate base, or vice versa. So if you have a weak, you can have a combination of a weak base and its conjugate acid. That's going to make a buffer solution. So buffers are this combination of weak acid and its conjugate base, or a weak base and its conjugate acid. And when I have that combination, that particular scenario can resist changes in pH. And that's because that weak acid can react with a base. If a base is added to it to keep the pH relatively constant, or if I add an acid to it, that conjugate base can be used to keep the basicity constant, because if I add acid to it, that base will react with the acid. So whenever you have that mixture, weak acid, conjugate base, or a weak base and its conjugate acid, you will have a buffer. And that's because the combination of those 2 species can resist changes in pH if I add more acid or if I add more base. So if I add an acid, which is a source of hydrogen ions to this. So let's consider this. If I add protons, just Le Chatelier's principle, right? If I'm adding more protons to this, or if I add a strong acid, let's get the pen out here. So if I add a strong acid, this concentration is increasing. What is that doing? I could produce more of that weak acid. So those protons will get used up because they will react with the conjugate base and they will produce more of that weak acid, which will resist the change in pH. So adding the source of protons will shift the equilibrium towards the reactants, which makes more of that weak acid. However, if I add a base, which is a source of hydroxide ions, so remember, hydroxide ions will react with the protons in order to make water. So if I add hydroxide ions to this, my concentration of hydrogen is going to go down. And if that concentration is going to go down, Le Chatelier's principle says that I cannot produce any more reactants. I will have a shift toward the products in this case. and therefore I would produce more of this acetate ion. So this is acetic acid. Again, not that you really need to know this, but sometimes it's nice to put a name to a formula. And this is the acetate ion. Notice Le Chatelier comes back a lot, right? I would say for your free response questions, I want you to get very comfortable with mentioning Le Chatelier, Le Chatelier's principle, Coulomb's law, right? You should reference Coulomb's law, and we're going to get more practice with this as we do more sample problems. But it all comes back to this Le Chatelier. So because of this, if I add a strong acid or a strong base, because of Le Chatelier's principle, these buffers will resist the change in pH, and it will keep them stable for a longer period of time. There's a lot of deriving here, right? And you don't even need to be worried about this because you are not responsible for knowing the derivation. However, if you want, you could take a look at this, right? Because it kind of works you through the derivation. This is what you need to know. This guy right here. And this is on your blue sheet. This is the Henderson-Hasselbalch equation. And this Henderson-Hasselbalch equation will tell us the pH of a buffer. So I could calculate what's the pH of a buffer solution by plugging in the pKa of that weak acid and take that and add that to the log of the conjugate base, the concentration of conjugate base, divided by the concentration of the weak acid. So let's go ahead and do some practice problems with this. I think this equation is easier to do some problems with than it is to talk about it. And you know I say that a lot. It's just, let's not talk about it. Let's just do it because I think it makes more sense that way. So we want to know, and I'm actually going to write Henderson-Hasselbalch up here again. So pH is equal to the pKa plus the log of the conjugate base, divided by the concentration of the weak acid. So I'll put HA. That's what we're going to use to calculate the pH of a buffer. So we want to know what's the pH of a buffer that's composed of 1.5 molar chloroacetic acid and 0.1 molar of sodium chloroacetate. So the Ka is 1.3 times 10 to the negative third. You could write an equation out for this, but I really don't even think you need to. We'll do it anyway, because why not? That's an equilibrium with, I have some protons, and now in this case, notice it's sodium chloroacetate, right? This sodium is a spectator. So you don't need to include that in your reaction. So I'm just going to show this hydrogen in the front is dissociated. And this right here is my chloroacetate. So if I want to know what's my concentrations, my concentration of chloroacetic acid is 0.15 molar. And my chloroacetate ion has a concentration of 0.1 molar. Like I said, that sodium's a spectator, so you don't have to worry about that. If you add that sodium, chloroacetate, sodium's dissociating. It's not involved in the reaction. It's just watching. So all I need to do is just plug this into my equation to find what's the pH of this buffer. So the pH of this system is equal to the pKa. Now remember, the pKa is equal to the negative log of the Ka. So I have 1.3 times 10 to the negative third. So negative log of that plus the log of my conjugate base concentration. So in this case, the conjugate base is 0.1 over my conjugate or my weak acid concentration, which is 0.15. And if you correctly solve for this, which I recommend you do, you should get a pH of 2.71. That would be the pH of this particular buffer solution. We're just using that Henderson-Hasselbalch equation, plugging in a couple of things and solving from there. Next question says calculate the pH of a buffer that's prepared by adding 10 mils of 0.1 molar acetic acid to 20 mils of 0.1 molar sodium acetate. So let's write an equation out again. So I have HC2H3O2, and that's in equilibrium with a proton and the acetate ion. So in this case, I am given specific amounts and concentrations, but I am doing a mix here. I am adding two solutions together. So it says I have 10 milliliters of 0.1 molar acetic acid, and I'm adding that to 20 milliliters of 0.1 molar sodium acetate. Now remember, I don't have to worry about the sodium because that's a spectator ion. I can't just plug in these concentrations into Henderson-Hasselbalch. And why not? Because I haven't actually done the dilution. When I put these two solutions together, I want to know what's the concentration of acetic acid in 30 milliliters of solution and what's the concentration of acetate in 30 milliliters of solution. Why 30? Because 10 plus 20 gives me 30. So if you do a quick M1V1 equals M2V2, you can find what's the concentration for each of these. And I did that for you here. So you should find that your concentration of acetic acid is 0.003 molar and your concentration of acetate is 0.067 molar. So now you have the concentration of each of those in the solution. You could set up an ice chart if you want, but your Ka is going to be so small, so you don't even have to worry about setting up that because you're going to have to neglect that X anyway. Let's go ahead and solve for this now that I have the concentrations. If you look on that paper I gave to you, because unfortunately I didn't list it here, the Ka of acetic acid is 1.75 times 10 to the negative fifth. So let's plug this into Henderson-Hasselbalch. The pH of this buffer is equal to the negative log of 1.75 times 10 to the negative fifth plus the log, my conjugate base concentration is 0.067 over 0.033. And if you solve for that, you find that this has a concentration, or a pH, of 5.07. Notice the only difference here was that I did have to perform that dilution because it's not giving me, unlike this first one, I have the concentrations. This buffer has these concentrations of the two species in it. For sample problem 9, it tells me I am adding some amount with some concentration to some amount with another concentration. So do be cognizant of what the particular question is asking you to do. Let's look at sample problem 10. This one's a little more intense, but I think we can do it. Instructions for making up a buffer say to mix 60 mils of ammonia with 40 mils of ammonium chloride. So it's asking, what is the pH of this buffer? This particular example, this is a base. Okay, so I would get familiar with recognizing the fact that ammonia is a base. And you could tell that it is a base because in this particular other species, it has accepted a proton. And we know bases accept protons, so this has to be a base. Let's write the equation out. Because this is a base, I'm going to react this with water. And I form ammonium. And that the hydroxide ion. So I just wrote just the regular basic reaction out. And I'm going to write down what I'm given as well. So it says I have 60 mils. Oops, I had another zero there. That's okay, but we'll erase it just in case. 60 milliliters of a 0.100 molar ammonia solution. And I mix that with 40 milliliters of a 0.100 molar solution of ammonium chloride. So ammonium compounds are very soluble in water. Therefore, this will dissociate. That chloride is a spectator. Okay, so notice there's no chloride in this reaction. It's because chloride is spectating. I do have another dilution that I have to perform. So I'm going to set up a line here and let's figure out, okay, if I have 60 mils of this at a concentration of 0.1, when the total volume's 100, what's the new concentration of this? And I would find that it's 0.060 molar. And this guy is 0.040 molar. I should have given you the KB for this because this is a base, but you can also look it up on that paper that I gave to you. Because if you're not given a KA or a KB and you need it, just look on there. It's got most of them listed. The KB for this is 1.8 times 10 to the negative fifth. Now notice that this particular example has a KB for it. So what I would recommend doing is I would convert the KB to the KA just because I think that makes life a little bit easier. So let's find out what's the KA for this particular reaction. Because remember, the KB is going to be much higher because this is a base, but I can in fact calculate the KA. So to find the KA, of course, we know KW equals KA times KB. KW is 1 times 10 to the negative 14th times KA, and the KB, I know, is 1.8 times 10 to the negative fifth. And if I solve for that, I find that the KA is equal to 5.6 times 10 to the negative 10th. Now that I found the KA, I could plug this in to my Henderson-Hasselbalch equation. So let's do the pH of this buffer is equal to the negative log of 5.6 times 10 to the negative 10th, which remember gives us the pKa, plus the log. Now, in the original problem, it says the conjugate base over the weak acid. You're always going to have base over acid, right? So when I'm solving this, even though I'm working with a weak base, I still have to put the concentration of the base on top. So in this case, I would do log of 0.060 over 0.040. So it's always base over acid. That's how I remember, base over acid, whether it's conjugate base, weak acid, or base conjugate acid. Okay. And if I solve for this, I would get a pH of 9.43. And this makes sense. I would always double check to make sure that your final answer works with the conditions of the problem. Ammonia is a weak base, so it should have a pH that's a little bit greater than 7, and it does in this case. So this is good. Let's talk about a little bit more with this. So something else you need to recognize, that diluting a buffer does not affect the pH. The reason why is because if you consider the Henderson-Hasselbalch equation, so if I have that the pH of a buffer is equal to the negative log of Ka, or the pKa, right? We'll write pKa out instead, plus the log over the base over the acid. I'll write this here too. No matter what that ratio of concentrations are, let's say my weak acid concentration is 0.1 and my conjugate base concentration is 0.1. Log, so this would give you 1, and the log of 1 is going to give me 0, right? In this case, the same thing, 0.5, if my weak acid's concentration is 0.5 and my conjugate base is 0.5, that's also going to give me 1. And the log of 1 is going to give me 0. So no matter what this concentration is, if you dilute a buffer, that buffer is not changing in its pH. And that's because it still has the same ratio of weak acid to conjugate base, or weak base to conjugate acid. So this ratio stays the same, which is what it says down here. So the ratio of conjugate base to weak acid does not change. Therefore, the pH is not changing. The higher concentration of buffer, however, has a higher buffer capacity. So let's say I have a higher concentration. So if I'm comparing that 0.1 molar to weak acid and conjugate base to the 0.05 molar concentration of weak acid to conjugate base, yes, they have the same ratio, so the pH is not changing. But if you consider this, think about stoichiometry, right? The higher the concentration, means that this particular solution has more buffer capability. This solution can buffer, or this mixture can buffer a solution with the addition of more acid or base because the concentration is higher. And we say that that has a higher buffer capacity. It could buffer a solution for a larger range of addition of an acid or a base. So I can add more base to that top scenario, and it will resist the pH for a longer period of time because it is more concentrated. And that makes sense. Think about stoichiometry and limiting and excess reagents. So we say that that has a higher buffer capacity. It can resist changes in pH over a longer period of time. So how do I make a buffer solution, right? And we're going to make a buffer solution in class. Hopefully it's a nice and easy lab. But there's Henderson-Hasselbalch again. We know that we can make the best buffer, the buffer that's going to resist the changes for the longest period of time, when the concentration of the conjugate base and the concentration of the weak acid should be about the same. So if I have some weak acid, if the concentration of this and the concentration of this is about the same, that means that I can add quite a bit of strong base to this, because that strong base will take this away and produce more of this guy. Or if I add strong acid, it will react with those protons and produce more of this. So if those concentrations of weak acid to conjugate base or weak base to conjugate acid are the same, they can resist the changes for a longer period of time. That makes a good buffer. So we know that the best buffer solutions, okay, if I have the concentration of the conjugate base, if that's equal to the concentration of the weak acid, we know that my ratio is going to be 1, right? Because if they're the same, whatever divided by whatever is going to give me 1. Log of 1 gives me 0. So we know, how do I know what buffer to use, right? Let's say I need to make a buffer that has a certain pH. How do I know the best buffer to choose? We have to look and see, well, which buffer has a pKa that's around 3.8? So what acid would be a good choice to make a buffer with a pH of 3.8? What we have to do is we have to look at that chart of your Ka values. And if you look up the pKa's, which one of those acids, or which two of the acids, has a pH that's closest to 3.8, you should have formic acid, or you should have lactic acid. Formic has a pH, or pKa rather, of 3.75, and lactic there's a pKa of about 3.86. So if I have this buffer with that pKa, we know that that concentration of conjugate base to weak acid is going to be the closest. And therefore, if that ratio is the closest to 1, it will resist the changes in pH for a longer period of time. So because these have a relatively equal ratio of A-1 and HA, these can resists changes in pH longer. So this will have the better buffer capacity, or the higher buffer capacity. If I were to choose something that has a higher pH, well, that means that there's more acid there, that the concentration of weak acid is higher than its conjugate base. So you're not going to have as good of a buffering capacity. And actually, on that note, let's take a look at this little chart right here, because this is important. And actually, now that I'm looking at it, it's bothering me that I italicized that and I didn't underline it because it doesn't match here, but whatever. Let's say that your concentration of your weak acid is stronger or is higher than the concentration of your conjugate base. So here, the acid has a higher concentration than the base. What does that do, right? If you consider Henderson-Hasselbalch, right? If your acid has a higher pH, and I just plugged in arbitrary numbers. I just did 1 and 2 just because it makes it easy. You'll find that your pH is lower than your pKa. And that makes sense. If the pH is lower than the pKa, that means I have more acid that's present in this particular system, in a titration, whatever. You have more acid particles that are present than the conjugate base. And that's when the pH is less than the pKa. Let's say that your solution pH is greater than the pKa. This means that your base has a higher concentration. So again, I have base over acid, according to Henderson-Hasselbalch. So when I solve for this, I find that this particular value equals 0.3, and therefore my pKa will be less than the pH. If the pH is greater than the pKa, that means that I have more base present. So my concentration of conjugate base is greater than my concentration of the weak acid. Here, my concentration of the weak acid is greater than my concentration of that weak base. And this can be a little tricky to understand at first. So I'm going to try to do as many practice problems as we can. I have an activity you're going to do with this. There's a poster you're going to do with this. There's a lot of different stuff. So if you're like, what in the world is she talking about? That's okay. We're going to practice with this because this test is so heavy on buffers and you have to know buffers and you have to be good at buffers. We're going to practice this a heck of a lot within the next week or so. That's where I'm going to end this video. I'm sure you'll have some questions and I will accept those questions whenever I see you again. In fact, I look forward to them because I want you to get nice and comfortable with this. As always, I was going to say, if you have any questions, let me know, but I already said that. So I will see you in the next video, which I think will be, we'll get into a little bit of stoichiometry with acids and bases. I will see you then. Bye.